Our second speaker is Chelsea Harris, who studies astrophysics at the University of California, Berkeley. Her advisor is Peter Nugent, and her practicum was at the National Renewable Energy Laboratory.
Is it on? Awesome. Hey guys. So since we're in DC in 2017, I changed my title to something more Kubrickian. So it's now Circumstellar Interaction, or How I Learned to Stop Worrying and Love the Stellar Bomb. So that is what I study, stellar explosions. So here's an artist's depiction of a star exploding. And the important thing that I need you to remember about supernovae for the next 15 minutes is that even if you have different explosion mechanisms, because a star exploded, you have like a solar mass of material. The ejecta speeds are really high, so a significant fraction of the speed of light. Although we don't need to use relativistic equations to describe the motion, I just want you to know it's really fast in case you don't have an intuition for 10,000 kilometers a second. And the actual light that we see on Earth is from the decay of radioactive material that is synthesized during the explosion. So if you have an explosion but it doesn't have radioactive material, you might not see it. But there's enough radioactive material that these guys can get as bright as an entire galaxy, which is like 100 billion stars if you're a Milky Way-ish thing. And they take about a month to for that radioactive material to diffuse through all that solar massive stuff. So this is a very famous supernova 1987A that I'm just going to use as a backdrop because of some interaction that's going on here. But to motivate, everyone thinks giant space explosions are cool, but they are also useful because they are the endpoints of stellar evolution. So if you want to know what stars are doing throughout their lives, you really need to be able to match our observations of how they die. They create and disperse all the heavy elements, so all that wonderful vanadium, that's supernovae, you're welcome. They inject energy into galaxies, as was mentioned earlier, because you have all this fast mass and you also have high energy particles. And they're useful as cosmological tools for getting this little curve here, right? The acceleration, Nobel Prize winning stuff, whatever, no big deal. But in order to do these three things, I'm all weird with the mic, sorry. In order to do these three parts in particular, you really need to hone down your understanding of which stars make the different supernovae, which is called the supernova progenitor problem. So in order to attack that problem and figure out, once you've seen a supernova, which is just a stellar death, and you often can't directly image the star that actually exploded, what we do is sometimes referred to as supernova forensics, because it's kind of like you're trying to solve a murder. And so if you're like me, you like little murder mystery shows, and you know, based on these highly accurate depictions of forensic techniques, that one thing that you can do is you can say, okay, what was happening to the Vic right before, the death? And so we try to do the same thing with stars. What was happening right before the star exploded might give us clues as to what caused the star to explode, and it might give us a clue as to what type of star it is, because the stars nearby are not exploding. Galactic supernovae are extremely rare. And so in order to get this sort of timeline, one tool that we use is to look for the impact of that fast ejecta with material that's surrounding the star that's called circumstellar material because it's around the star. You are actually familiar with the fact that stars lose mass, even if you maybe didn't think of it that way, because we have these pretty little lights called the aurora borealis, and this is caused by the stellar wind, the sun's winds, the solar wind interacting with Earth's magnetic field. It's a really puny wind, but it's analogous to stronger winds from other stars. And then also, if you look up pretty space pictures, sometimes you'll see things like planetary nebulae, which are created from the ejection of the envelope of a star. So stars lose mass pretty regularly, and these types of processes and instabilities are what could cause it to have material surrounding the star. And if we can find a way to characterize how this material looked without directly imaging it, then we could compare it to examples in our galaxy of stars to do that correlation. of, this supernova had circumstellar material that looked like this, therefore it's a star that looks like this, or something like that. So to explain the physics of circumstellar interaction, I'm going to use a supernova remnant, which is a supernova interacting with the interstellar medium. So this material is not associated with the supernova progenitor star, but the physics is really similar. So in this HST and Chandra image, the blue here is the radioactive material that's seen from the ejecta that's seen in the X-rays. And then you can see that shock front from the ejecta hitting the interstellar medium in pink. That's the H-alpha line. The ejecta is able to form the shock because it's a strong shock because it's moving so much faster than the CSM. So, and also because it's moving so much faster, it's able to sweep over a long period of mass loss history in just a few years. So we don't need to observe it for 1,000 years to see the last 1,000 years of mass loss. So in that way, it's kind of like a time machine. It's kind of rare to actually see a supernova interact with the circumstellar environment, in part because you need to have a really dense circumstellar medium. So like our solar wind is like 10 to the minus 14 solar masses being lost every year. When we measure a supernova interacting with circumstellar mass, in the canonical cases, it's like 10 to the minus 2, so a factor of 10 to the 12 higher mass loss rates. But because the circumstellar medium can be built up from binary processes, which, if you've noticed, our sun isn't in a binary system, so we don't really have a way to learn about that from our sun, but if CSM is from a binary process, then if we can constrain that circumstellar material, it might tell us about how binary systems interact and cause mass loss before death, which is something that's theoretically pretty hard to constrain from the computational models. Okay. So as I said before, the physics here is that we're going to have fast ejecta colliding with slow surrounding gas driving a shock. The shock compresses the magnetic fields in a thin region, and the magnetic fields accelerate through turbulence, we think, electrons to relativistic velocities. So this is a non-thermal environment in the shock front. And these guys are nice because they emit a bunch of different wavelengths. So those familiar with astronomy know that depending on what your photon energy is, you have to use a totally different instrument to observe it. And so if you can get, and these probe different regions. So the X-ray and the radio probe your non-thermal electrons, so that's the shock region, whereas optical and UV and infrared probe more like a reprocessing of those high energy photons in the ejecta or in the circumstellar material outside of it. And the infrared can tell you if dust is formed, which is useful because we don't know how dust is formed. So the goals that I had for my thesis were to basically move away from the model that we had long been, I'm going to say, stuck with, which is that you just have a wind emanating from the surface of the star and at a continuous mass loss rate, which, FYI, not ever seen. So we were just using this really simplistic model. And in particular, I was interested in whether interaction signatures could be really short duration, so that you get an observation and then you wait like 2 weeks to get another one, and maybe you just miss the interaction during that time. If you had a continuous wind, you'd say, oh, that's not a problem. But if you have a brief interaction, then you could have just missed it, and you're not really constraining the CSM at all. Interaction that is delayed in time because the circumstellar material is detached from the stellar surface. And then, in particular, non-spherical interaction. So instead of saying that it's like a spherical wind emanating from the solar surface, then maybe it's something like a disk or lobes, which are observed in mass loss systems. And the important thing also to me is to predict the non-thermal radiation signatures and the line luminosities instead of just doing the typical thing of saying, okay, I have a shock dumping in energy, let's just say all that energy comes out or it's diffusing through. If you don't have a high enough density environment, you might not get that diffusion you're looking for. So having accurate predictions in my synthetic radiation signatures is something else that I thought would be really important to give to the field, especially as we move into the era of like LSST, where we want to basically be data mining. So we need to have good models of what we expect these events to look like, because as I said before, they're pretty rare. So I'm supposed to talk about HPC. Primarily what I want to say is I've been trying to avoid it my entire thesis because these systems it's not really known what the CSM would look like, so I need to explore parameter space. And to do that, I need to use simple models instead of trying to do all of the complexities of a full 3D hydrodynamic model. I want to save that for the most promising model, so just like dumbing it down at every level was kind of my goal. And in particular, the reason that doing this problem right would be challenging from a high-performance computing standpoint is because you do need to do the hydrodynamics. We use basically a moving mesh or Lagrangian scheme for solving the hydro, but you'd really want to do it in 3 dimensions so that you can see all the neat effects of mixing the ejecta, which might be metal-rich, with the CSM, which might be metal-poor. And then you need to, in addition to the hydrodynamics, do radiation transport of photons, which requires that you solve the ionization state of the gas and the electron level states, especially important if anything's neutral, anything that's bound. You really need that information to get line luminosities, which are often very critical indicators when evaluating supernova observations. And then you have to do the photon transport, which we do with a Monte Carlo method. So you have to generate the photon somewhere and then let them kind of bounce through the model according to this stuff that you calculated before. And so this is a model that I'm actually working on right now. I didn't do the hydrodynamics. Those will be presented in a different paper by a different Berkeley group, but I'm just doing the post-processing radiation transport. So by decoupling these steps, you save yourself some of the HPC, the computing load, because you're not trying to couple these while you go. And so in this case, we have ejecta, which would be spherical, except it's colliding with a shell, a ring, of circumstellar material, so it creates this nice lobe shape. And the interesting thing is here, if you're looking down from this direction, could you just not see the interaction at all? You're just like, wow, that supernova is weirdly bright because you're getting extra energy deposited, which is important for things like, for instance, constraining the nickel mass. So just to present one thing that I did that illustrates sort of this stuff coming together, and also why doing things that aren't computationally expensive is important, is a confined circumstellar shell. So again, instead of doing a wind that just extends off into infinity, I say I have some ejecta on the inside, and then a really narrow shell. This would be that short duration interaction because the shock wave will quickly sweep through the shell. Then outside of that, I put some vacuum zones, basically just for boundary conditions, And so in the panels here on the left, you'll see the hydrodynamics. It's the log of the internal energy density of the gas. And so right now you really can't see anything because the circumstellar material is cold. But when the shock starts, you'll see this spike up and the shock propagate through the circumstellar material. And then at the same time, you'll see the radio light, which tracks the shock energy. And this would be my observable. And you'll see how that gets built up from the hydrodynamics. So the shock gets built up, and then it escapes the CSM, and you get an energy drop. 2 things that you can't just necessarily do analytically that the computational models are important for are predict the... You know what? I'm going to take that back. I bet you can analytically predict this rise, which is just the buildup of the volume of the shock region because nothing's cooling because it's low enough density. But what's really important, especially if this shell was thinner so that the interaction is faster, is that you have this tail. That gives you basically extra bright time. And if you say that this just cuts off here and then you try to say, what was the probability that we would have detected a shell, you can be off by, like a factor of 2 or something, which in this case is important because in some cases you would predict a shell, so you want to have accurate constraints on the existence of that circumstellar material. And so I did this in 1 dimension because then I didn't have to do a bunch of 3-dimensional calculations. I don't like 2D for Rayleigh-Taylor instability, so I'm not even going to mention 2D, 3D or 1D. So in this case, because I'm doing these 1D things that go really fast, I'm able to explore parameter space, changing the shell width, its distance from the supernova, and its intrinsic density. So just as a plot here, this is changing the density, and this is changing the distance from the supernova, and I'm just like, look at all these models that I have. So that's ignoring one dimension that I changed, which you can make a plot like this in 3D because you'd have like one point that you just know really well. But because we don't know what these properties should be, especially because we've never observed it in a supernova collision, again, that arguable for 11kx. Anyway, it's important to explore parameter space. And the nice thing was that these light curves, so this was the first light curve that you saw in the radio. This was for a relatively thick shell, and then if I changed the shell width, what I found is that they all obviously follow the same rise, which you would expect, and then the way that they decline, you can parameterize really simply, such that you don't even need to run more models. So what I did was I just found a way to parameterize these light curves, which means that you can very quickly generate the radio light curves in any band, as long as there's not absorption. And so what you can do then is you can analyze your observations more accurately. So this is a supernova 2011 FE that famously has a very clean environment, and all I'm doing in this plot is I'm saying, okay, for different shell widths and different luminosities that they peak at, what would have been the probability for a certain set of observations to have seen a shell? So you can actually just say, we know there wasn't a nova shell in supernova 2011 FE to this confidence for this property, which is something that we couldn't do before. And then if you were to just constrain the shell width, you can change the luminosity into a density. So I showed that for another nearby supernova, 14J. And you change this then into an observation probability plot versus a density of the CSM for a thin nova-like shell, so that you can say things like, to 50% confidence, we know there wasn't a shell that's like a millionth of a solar mass. And to 90% confidence, we know that this isn't a system like the observed interacting system PTF11KX, which would have fallen here. So those are important things for us to be able to say, especially as you get into this era, again, of big data. It's important to be able to make these types of do this type of analysis very quickly, because you might not just be analyzing one supernova. So I'll end there, I think, on time, with the typical thank yous. But Krell has been especially great. I can't believe Lindsay's patience with me, because I can't turn in anything on time. And I really appreciate how people fight so much for us to get funding and seem to be really proud of us, even though that's overwhelming sometimes. I did my practicum at the National Renewable Energy Lab, and I have a picture here of one of the little projects that I did at the end, because they have like this 3D projection room. So I was working on heliostats, which is this big mirror here, which project light, in this case, onto this cylindrical, or this tube in the center, and that's how they get solar energy. It's converting it into heat. And I was studying the whole grain defect thing that Kathleen mentioned earlier affects these mirrors, where they slowly degrade over time and lose their reflectance. And so we were trying to model that, which is just a radiation transport problem. So I was like, perfect. But the really cool thing was being able to make this outreach thing where we could model a heliostat and show it degrading, and then, people who come in who don't know anything about science but maybe would be interested in funding this technology can go in and put on the 3D glasses and kind of like play around with the heliostat properties. Thank you guys. You are really cool, and I've enjoyed hearing about your research and just hanging out with you. And of course, Peter Nugent, who is here, thanks for being such a great advisor and tolerating me for so long. That's it.